Okay, thank you very much. And I'd really like to thank the organisers for giving me the chance to speak here and for all their incredibly hard work in organising such a big conference. Yeah. So this talk is kind of going to have two halves to it. The first half is going to be basically a review of the behavior of the wall crossing formula for DT invariance. So that's work of Joyce and Kontsevich and Soibelman. Probably familiar to quite a few of you, but I want to explain it as clearly as I can. And then in the second half, there are going to be these Riemann-Hilbert problems, which are a more sort of experimental piece of mathematics, although they're very much inspired by work of Gaiato, Moore, and Knightsky, although it's not quite the same thing that I'm going to be doing. Okay, so there are some preprints here, which cover pretty much everything I'm saying in this talk. So I'm not going to give you all the details of the calculations and so on, but you can find them in those papers. So there's just going to be one slide of motivation. You know, as you write a talk and then at the end you think, oh, you better put some motivation at the start. So I did this. I'm not sure how much sense this page makes, but we'll try and get through it fairly quickly and go on. So what I'm thinking about is that there are two types of parameters that we think about in string theory. Basically, typically we would think about them as the complex parameters of our Calabi-Yau threefold or the Kähler parameters. And depending on whether we're thinking about the A model or the B model, these are deformation parameters or stability parameters. So for example, if we're thinking about the B model, which is usually my favorite, so we're thinking about coherent sheaves, then the complex structure are the deformation parameters. That tells us which category we're talking about, the category of coherent sheaves on which complex manifold. And then the Kähler parameters arise as stability parameters. They pick out special classes of objects like stable vector bundles, for example. And there is some more global theory, this theory of stability conditions. But these things are exchanged by mirror symmetry. I mean, if you start thinking about the A model, then what were previously the deformation parameters become the stability parameters and vice versa. Okay, so we know that the space of deformations carries some natural variation of Hodge structures. So, I mean, if you're thinking about this classically, you just have some family of complex manifolds, you have a variation of Hodge structures. There are more souped up versions of this to do with deformations of categories. But the question I'm wanting to ask here is, I mean, given that the deformation space also arises as a stability space on the opposite twist, you should expect that over the space of stability parameters, there are also natural variations of Hodge structure. And the question is, can we get at those? You know, can we define those directly? So we're looking for interesting geometric structures on these spaces. And the obvious data to use to try and get at these is Donaldson-Thomas invariants, actually, because those are if you give me a category with a stability condition, the one thing I'm supposed to be able to compute is DT invariance. Okay. I mean, another reason why this is kind of the right thing is if you think about the Kähler moduli space, we usually define a variation of Hodge structures on that, so-called A model variation of Hodge structures, using genus zero Gromov-Witten theory, right? Now we know morally that DT invariance, if you think about ideal sheaf DT invariance, they encode all those Gromov-Witten invariants via this DT Gromov-Witten correspondence. So we can kind of expect that the DT invariance should be able to see that A model variation of Hodge structures. But somehow what I'm trying to do here is something more global. I mean, you know, that A model variation of Hodge structure is just on the Kähler cone. It's just near large volume, whereas there is an interesting space, this stringy Kähler moduli space with some topology, and one would like a kind of a global construction on there. And for that, Gromov-Witten theory is kind of too geometric. This DT theory is better. However, I mean, we understand how to get from Gromov-Witten invariance to a variation of Hodge structure. It's to do with the special properties of the compactification of M0 n bar. And nothing of that applies to DT theory. Instead, the fundamental property of DT invariance is really this wall crossing formula, which I'm going to explain. That's really what you have. And so you need to understand that property better and see how it could lead to some geometry. And the key thing to bear in mind is, well, which I'm probably not going to explain very well here, is that there is a strong analogy with the story of Stokes data and iso-Stokes deformations of differential equations. Okay, so that was some very sort of up in the air motivation. Let me get on to some more concrete stuff. Okay, so I'm going to introduce this thing called a BPS structure. It's a terrible name, and I'm sorry about that, but it is at least a concrete thing. And the point of doing this is it means I don't have to tell you the whole theory of DT invariants and how to define them. So this is going to be, I'm just going to tell you what the output of DT theory is. And here it is. So what you have is you have some abelian group, free finite rank abelian group, equipped with some skew symmetric form. You also have a homomorphism of abelian groups called the central charge. You could call this thing the charge lattice. And a map of sets which is encoding the BPS invariants. So normally we would expect these to land in the integers, but you know, we often struggle to prove that, so for now we're just going to take those to be in the rationals. And there's a couple of conditions which are not very important at all, in fact. Firstly, there is this symmetry property that if you change the sign of the class, you get the same BPS invariant. And there's this thing, the support property, which is a little bit technical and won't play any role, but let me just sort of explain something about it. It says that if you fix a norm on your charge lattice, then for objects, for classes with non-zero BPS invariant, there is some inequality like this. And morally, you should think of this as just saying that the classes, I tend to call a class active if it has non-zero BPS invariant, that the active classes, their central charges don't cluster at the origin. Okay, that's basically what this is saying. Or in other words, if you restrict the radius of Z, that Z gamma is, you know, if you look at all the things satisfying Z gamma in some ball, then there are only finitely many classes. That's what that's saying. So yes, so from the point of view of mathematics, how do you get one of these things? You take your CY3 triangulated category, you take a stability condition on it, then this charge lattice will essentially be the Grothendieck group, this will be the Euler form, this is the central charge, which is part of the data of the stability condition, and then this is the interesting stuff. This is the DT invariance that you've defined using some very difficult theory developed by Joyce and Kontsevich-Soibman. Okay, so this is some rather, I mean, here, there's nothing difficult here. The interesting thing is the way these change as we move the central charge, which we'll get onto. Okay, any questions about that? No, good. So let me just give you a concrete example. So this is the one arising from the conifold. So I take my lattice to be two-dimensional. The form is going to be 0. That's because the intersection form on, yeah, I mean, everything on a conifold is basically supported on the curve, and curves don't intersect on a threefold. And then I have to choose some central charge, so I've chosen it more or less randomly. And then these are the correct BPS invariants. And here's the picture that goes with it. So more important than the example really is the picture. So what am I drawing here? This is the complex numbers, and I'm drawing Z of gamma, the image of the central charge, applied to every class with non-zero BPS invariant. Okay, so there are these classes 1, D, and these go along here. And then there are these classes 0, D, and these are going along this axis here. Of course, geometrically, what you should think here is that the resolved conifold has a single P1, single rational curve. These things are the line bundles on that rational curve of degree D, and these are the points on the conifold, so, well, unfattened points. So these are zero-dimensional sheaves on the conifold. Okay, so that's what the DT theory gives you. Are we happy with that? So this sort of diagram is good to bear in mind. I call it the ray diagram, and these things I call the active rays. These are the things spanned by Z of gamma where gamma has non-zero BPS invariant. Okay, so in order to state the wall crossing formula, I need to introduce some, just some data. So we introduce a torus, an algebraic torus, whose character lattice is gamma. Okay, so it's a copy of C star to the n. Here's its ring of functions, some Laurent series, Laurent polynomials. And the fact that you have this skew-symmetric form on gamma, that induces some invariant Poisson structure on this torus. Okay. And there's a small technicality here, which I suggest you completely ignore, which is that more precisely, for this to work, you should be working with some torsa over this torus. So, I mean, this algebraic torus would be defined by the condition that f of gamma 1 plus gamma 2 equals f of gamma 1 times f of gamma 2. This thing has this annoying sign put in there, which just means that there are various signs come into the formulae. They need to be there, but let's not worry about it in this talk. Okay, this is related to what people call quadratic refinements of the form. Okay, and then, right, I should have paused halfway here. So now I want to introduce some formal functions on this torus. So first off, I want to define some related invariants to these BPS invariants just by what in Gromov-Witten theory would be called a multiple cover formula. Here it's not a multiple cover formula. So what does this formula mean? It means that if gamma is a primitive class, then this sum only contains gamma, so we have that dt gamma equals omega gamma. It's only if gamma is divisible in this Grothendieck group that you get more terms coming in here. So it's kind of some equivalent way of re-expressing these BPS invariants. And then I want to consider the generating function for these things. Okay, so given some ray, you can probably see if I mean, the one diagram to keep in your mind at all points in this talk is we have the complex of a bunch of rays, maybe countably many in general. And we have the images under the central charge map of the classes of, classes with non-zero BPS invariant. Okay, so now I can in this complex plane, and I can sum up the DT invariants with the appropriate character on that ray. Okay. So what you can see is that if there's only one non-trivial, if there's just one omega gamma living on this ray, then this is going to be a dilogarithm, right? Because that omega gamma is going to contribute to every dt n gamma with a coefficient 1 over n squared. So here you're just going to get a dilogarithm. Okay, so that's where the dilogarithms come in. And then what we want to do is we want to take this function on the torus and take the time 1 Hamiltonian flow. Okay, we've got some Poisson structure on this torus, so that makes sense. And that will define me some Poisson automorphism of the torus. Okay, that's the important thing we want to do here. Of course, this is a little bit dodgy because this is really a formal function, and taking time 1 flows, there's no reason why that flow would converge. So we have to work a bit to make sense of this. Okay, but I hope the idea is at least clear. So how do we make sense of this? There's kind of two ways you can do this. When you're stating the wall crossing formula, the best thing to do is just take a formal approach. So we were supposed to be working with the torus, so therefore with the ring of functions on the torus, which is this thing, Laurent polynomials. If we're only interested in classes lying in some positive cone, we don't need to consider all of that. We can just consider the polynomial ring. And then, of course, we can complete that and live in a power series ring. And then these kind of automorphisms make perfect sense of this algebra. Okay, so what I've written here, of course, is just the algebraic way of saying time 1 Hamiltonian flow. That's what the pullback of time 1 Hamiltonian flow does. It exponentiates the derivation given by Poisson bracket with dt of L. Okay, so the point is that this formula might not make sense in this ring, which is where we wanted it to make sense, but it will certainly make sense in this ring. So as long as we're only interested in classes lying in some cone, then this is the way to do it. That's not going to be good enough for us always. So we also need to do sometimes take an analytic approach, and there we're going to need some restriction on these BPS invariants, and the natural restriction to put is this one, which is that yeah, basically the BPS, there can't be too many BPS invariants. They can't grow too fast as the central charge goes to infinity. So if you put this condition, then you can show that there are analytic subsets of the torus on which this function converges and on which the time one Hamiltonian flow exists. Okay, so you can actually make sense of this on some analytic subsets of your torus. Now, I mean, this condition is a bit, I mean, I know physicists expect it to be satisfied in some cases and not in others, so I think you wouldn't expect this to be satisfied on a compact Calabi-Yau threefold. It's also not clear that it's preserved under wall crossing, so if it's satisfied at one point, it's not entirely clear that it will be satisfied at another. But nonetheless, there are tons of examples where it's just completely obvious that this is satisfied. For example, there may only be finitely many BPS invariants, so it's a good start. And if anyone has physical insight into this condition, I'd be very happy to hear about it. And so, just to make contact with probably the way you're more used to seeing this, so these maps are actually often birational automorphisms of the torus, and there's a standard formula for them. And the way you see that is you can actually compute this time one Hamiltonian flow. So you exponentiate this derivation. You can see that because when you do that, you're going to bring down a power of n. Sorry, you're going to bring down n because it sort of differentiates this, and that's going to turn into the power series for log. And so when you exponentiate it, you're going to get, you're going to get the power series for log 1 minus x gamma, and when you exponentiate it, you're going to get this term. So this is just a simple calculation. So now when a ray in the complex numbers satisfies these rather strong conditions, that there are only finitely many classes having non-zero BPS invariant living on that ray, these classes are all orthogonal, and let's assume that the invariants are also integers, then you really have just this formula, which I think is pretty familiar to lots of people who are studying this subject, that this automorphism of the torus takes this form on characters. Oh, and there's a missing x beta, and I do apologize for that. So there should be an x beta here. So it should be x beta there. So it multiplies x beta by this factor. Okay, so it's kind of important to try and remember this formula. Maybe the easiest thing would be to write it on the board, especially since it's wrong. Yeah, so the thing to bear in mind is that a character jumps by something which is here is the bracket of the thing you're interested in with the thing that is causing the jumping. So in particular, if something is orthogonal to the things that are causing the jumping, then it won't jump at all. That's sort of an important thing to bear in mind. Okay. So now we can talk about a variation of these things. So this is just going to be the wall crossing formula now. So what we want to do is think about a complex manifold, which is going to be morally like the space of stability conditions, for example. And you're going to have BPS structures as I've defined them at each point of this manifold. And there should be some conditions on how these vary. And the numbers, the central charges should just vary holomorphically. There's nothing surprising there. And then the crucial thing is, how do these BPS invariants vary? And this is the condition. It's the wall crossing formula. So what it states is that, if you take any convex sector in here, and you take the product of these automorphisms of the torus over all the rays occurring in this sector, then that should be constant as we vary the BPS structure. So as we vary the data, these central charges move around. So these two rays could easily collide, and then they could turn around and move in, and they could split into lots of different rays. But the condition is that this product always remains constant, providing you don't just do the stupid thing, which is just take one of these classes and move it over the boundary of your sector. I mean, that's not allowed. So that's this condition about whenever the boundary remains non-active. Okay. So I'll give an example which might say more than this formula, but the basic picture is that whenever you have one of these BPS structures, you have this picture in the complex numbers of a bunch of rays, and associated to each ray, you have an automorphism of the torus. And the condition is that as you vary this data, the product over these rays of these automorphisms of the torus should remain constant. Would anyone dare to ask a question? No. Okay. And the thing that's not quite obvious, I mean, it's not difficult to prove, but it's not obvious, is that if you give me these numbers at some point of my manifold S, then this will determine the numbers at all other points. So it's kind of an amazing thing. So it just says that the BPS invariants at one point determine the BPS invariants at all other points. So there's And I should just say, why have I said framed here? It's because I've kept this, this lattice constant. In general, you want to allow the lattice to form a local system over your manifold S, but that's not something we need to worry about. Why did I fix it? Just because it's easier to state this. Otherwise, this torus is varying, so you have to say that this is constant, covariantly constant with respect to the connection on the torus. That's kind of an unpleasant thing to have to say. And it's kind of a local thing anyway, so, and locally you can always trivialize. So, yeah. Okay, so let's just quickly see the standard example. So in this case, we just take a two-dimensional lattice with the two basis elements having bracket 1. So here's my torus. It's just, well, the functions is polynomial rings, Laurent polynomials in two variables. Here's the Poisson structure. Essential charge is determined by, obviously, by its values on these basis elements. I'm just going to assume that both of those values are in the upper half plane. But otherwise, I can vary them freely. So this is going to be my base of my variation. I'm just going to take S to B, two copies of the upper half plane, and that's how what the central charges are. And then I'm going to define BPS invariants like this. Depending on which way round, there's a picture on the next page, depending on which way round these Z1 and Z2 are, either there are two non-zero, well, essentially two non-zero BPS invariants, or there are three. Okay, it's really 4 or 6 because we have to, because of this symmetry property. And so here's a picture of what's going on. You should think of the manifold S, which is two copies of the upper half plane, is divided into two pieces by the wall. The wall is where these two ZE1 and ZE2 line up. So on one side of the wall, we have this kind of situation, this is to the right, and on the other side of the wall, we have this situation, Z of E2 is to the right. And in this case, you have 3 active rays, and in this case, you only have 2 active rays. This is dashed because it's not an active ray. The BPS invariant of this guy, E1 plus E2, is 0 on this side. So I shouldn't really have drawn that at all. Okay, and so this is the situation. And then the wall crossing formula is the cluster pentagon identity, which is this product of, we're just considering birational maps of this type, like we had on the board here. And the product of these two is equal to the product of these three. Okay, so that's the wall crossing formula. We've varied the z's. Things have changed when we cross the wall, but if we knew these BPS invariants, then this is uniquely determined. I mean, all we had to do was write down this product and then re-expand it as a product in the kind of opposite order, and there is only one way to do that, and that's the answer. So the reason this is A2 is because I had this bracket E1, E2 equals 1. So that's the adjacency matrix of the A2 quiver. If I change that to a different number, this situation will become much, much more complicated. On this side, I can start with the same data, but when I cross the wall, I will have infinitely many rays, and it's very complicated. We don't really understand the BPS invariants explicitly. We just know that they're uniquely defined by this wall crossing property. Okay, how are we doing? So I don't know whether this was familiar to most of you. That's the first half of the talk. So if there's any questions, now's a good time to ask. Okay. Okay, so now we, do I go straight into this? Yes, I do. So the thing to bear in mind is this picture. So we have a BPS structure. We have one of these, we have the complex numbers, a bunch of rays, and automorphisms of the torus associated to the rays. So what we're going to do now is look for piecewise holomorphic functions from this picture into the torus, which jump appropriately as you cross these rays. Okay. Right, so I'm going to start by fixing this data that we've been talking about all along, and I also need to fix a point of my torus. Right, and let's just, okay, so what we want to do is find a piecewise holomorphic function from C star to the torus, satisfying, this is the crucial thing, that it should jump when we cross one of these active rays. So let me just, that's the kind of same. The point is that associated to each of these things, now we have some SL1, we have some automorphisms of the torus. Right, so these are in. Okay, so it makes sense to ask for a function from this picture into the torus, which is holomorphic on these sectors, but which jumps as you cross precisely by this automorphism. Right, so that's the jumping, and then we also need behavior at 0 and infinity, because I'm wanting to try to get a unique solution. So this is the limiting behavior at 0. So it's easier to write it in terms of characters. Sorry for the extra bracket. So this is a map into the torus. Of course, I can compose with a character and get a map from C star to C star. So I'm taking the, I'm applying the character to this element of the torus. That's an element of C star, and I want that to satisfy, to have this behavior. I mean, maybe more schematic way of saying it is just that maybe that's a better way of writing it. Okay, so it has this sort of behavior. And where do you get that from? That's very much based on the analogy with differential equations and Stokes data for differential equations, which maybe I'll come back. But that's where you get the idea that that's a good thing to do. And then at infinity, I'm going to put basically just a kind of moderate growth condition. I'm asking that these functions, I compose with the character again, I get a function into C star, and I ask that it grows no faster than a power of t. Okay. So you would probably be happier if I called this parameter t if I called it epsilon, that would probably be a better thing to call it. But mathematicians have problems sending epsilon to infinity, so I think that's not something I can do. But right, so because I'm not doing the same Riemann-Hilbert problem as you are. But let me point this out. Yeah. So this is different. Yeah. So this is yeah. So what's the right thing to say here? I mean, so Gaiotto, Moore, and Knightsky considered a rather similar Riemann-Hilbert problem with exactly the same jumping condition and with exactly the same limit at 0. But they had a different behavior at infinity, which was essentially a kind of complex conjugate of the behavior at 0. Whereas I'm not doing that, I'm doing something definitely different. This corresponds, I think, to what physicists call the conformal limit of what you're doing. And it's in the analogous finite dimensional situation where instead of thinking about, so I mean, essentially what we're thinking about here is the infinite dimensional group of automorphisms of the torus. The finite dimensional situation would be just to think about a similar problem where you had the group was GLN. And you would have a similar picture, but associated to each ray, you would just have a matrix. That would be Stokes matrices. And in that situation, again, there are two stories, one of which leads to, kind of Frobenius structures, and one of which leads to kind of TT star geometry. And again, those, I mean, it's exactly the same story. You either consider connections with two irregular singularities, which are kind of complex conjugate, that's the TT star story, or you consider connections with one irregular singularity and one irregular and one regular, and that's the kind of Frobenius manifolds, Frobenius story. And so this is the second one. So I'm expecting my connection to have a regular singularity at infinity. That's somehow what's going on. Okay. So, I mean, it's rather easy to write this problem down. It's even cheaper than making a conjecture, writing down a problem, because you don't even say what the answer should be. But the key thing here is that you can actually solve this problem, at least in some interesting cases, and you can solve it uniquely, and that's what I'm going to tell you about. Okay, so let's start. So we had the A2 example, which some of you may have considered to be beneath you and too trivial. So the A1 example is even more trivial. It's the following thing. So we take a one-dimensional lattice. So the form, since the form is skew-symmetric, it has to be 0. The central charge, well, I just have to give you the central charge of the class gamma. That has to be non-zero. That's by the support property, in fact. And I'm just going to take one non-vanishing BPS invariant. Okay, so this is DT theory applied to the A1 quiver. The A1 quiver is a single vertex, so it's just the category of vector spaces. This is a really trivial thing. Okay, so the torus is C star, and we know that all these automorphisms have to be trivial because the form is trivial. I mean, these are time one Hamiltonian flows. The Hamiltonian vector fields are all 0. Nothing is going on here. So we can immediately see that there is a unique solution to the problem in this case, and it has to be given by this. I mean, it just has to be given by its asymptotics, which is this. Okay, so nothing interesting there. But now what we can do is we can double this BPS structure. So what that means is I make the lattice bigger by adding the dual lattice. Okay, now this thing has a canonical skew-symmetric form on it. Right, the obvious kind of non-degenerate skew-symmetric form on this thing. And I'm going to extend Z and omega by 0. So there's still only one BPS invariant. But now the form is non-trivial. Okay. So now it makes sense to ask, okay, I mean, this character is still what it is. But we have one more element of this lattice, which is the kind of dual basis element. And I can ask, what is that function doing? Okay. And so you just translate that Riemann-Hilbert problem, and what you get, yeah, I'm going to take this. and then you just get some condition. So remember, we're just looking at a picture like this, but there's only one ray. And so it should be holomorphic away from those rays, and it should jump. And remember, we said that the amount something jumps, you know, there is some thing here which is measuring the bracket of the class that's causing the jumping with the class you're interested in. So here, the class that's causing the jumping is gamma, and we're interested in the class gamma dual, so we get some 1 here. And we already knew, we had already solved this, the class that's causing the jumping, that's what that is. Okay. Because Z dual, we extended Z by 0, so this asymptotic just collapses. So it goes to 1. And we again have this moderate growth condition. Okay. So now this is a problem in a form you could give to an undergraduate. And the solution is basically the gamma function. So right, so the solution, it has 2 parts according to which side of this ray you're on, and the function you have to put there is this modification of the gamma function. Can you scale that? Yes. Yeah, you would just get the square of this. Yeah. I think that's true. I should check, obviously. Yeah, I maybe take that back. I don't know right on the nose what the answer is. So, so for your undergraduate to do this, all you would need to tell him is this, him or her, you would need to tell him this data. So yeah, I mean, you just have the Euler product formula and this Stirling expansion. And so, by the way, this explains what happened here, right? I mean, you insisted that your function had asymptotics 1 at the origin. And the gamma function doesn't have asymptotic 1. It has some funny terms at the start, and that you just got rid of those by kind of putting those into the function, and then you have an appropriate asymptotic. Okay. So, I mean, this is, you know, absolutely not surprising to physicists. I'm sure they, you know, knew this solution. That from a mathematical point of view, what's nice is that this is a very natural problem, and you can really just be very careful and prove that there is a unique analytic solution to this problem. And then you can easily bootstrap up to a more general situation. Did I do tau function already? Okay, yeah. So now I have to introduce something rather dodgy. I mean, again, I'm not sure whether I like the name. There was some reason for this. So I want to encode the solution in a function. So now I want to consider a variation of BPS structures. So my data is all varying, and I want to encode all the solutions to the Riemann-Hilbert problems in one function on the base. So let's imagine we're in this situation where we have what we discussed, a variation of BPS structures over the base, and I'm also asking that it's kind of universal in the fact that in the sense that the central charge is everywhere varying kind of completely. So the map from the manifold to the space of central charges is a local isomorphism. So this is the situation where you're talking about stability conditions. And if I take a basis, then we can think of these as local coordinates on my base. And let's suppose we have some analytically varying solutions to the corresponding Riemann-Hilbert problems. Then I want to define this thing. So basically what's happening here is that phi is a map into the torus. If I differentiate it, I get a map into the tangent space to the torus, but the tangent space to the torus is the same as the tangent space to S by this condition. And therefore I can look for a Hamiltonian function which gives you this vector field, and that's what's going on here. So, I mean, I must say this is just a kind of experimental business. this gives you the right answer. But, I mean, it's not such a bad definition either. Okay, so now what you can do, in the A1 case that we were just discussing, I mean, all you've done is you've taken your gamma function, which was this, you've differentiated it, and then you've integrated it with respect to a different variable, right? So no great deal. And indeed, you're just going to get a similar expansion that you had to the gamma function, but you know, this 2g minus 1 has changed to a 2g minus 2, basically. But if you want to do it properly in terms of the functions, what you're getting is the Barnes G function here. And now, whenever we have a BPS structure which is uncoupled, so this is a very strong condition. This is saying that for any two classes, for any two active classes, their pairing is 0. Okay. What that means is that the jump here commutes with the jump here, and it commutes with the jump here. So if I want to make a solution to my Riemann-Hilbert problem, I just take a function which jumps appropriately here, multiply it by another function which jumps appropriately here. I can just superpose those solutions, and I'll get a solution. It's kind of easy. And as long as there are only finitely many of these things, this is going to work precisely, and I'll get a unique solution to my problem. And the corresponding tau functions will just add. So this is the formula you get for the tau functions. It's just the sum of these weighted by some omega gammas. Okay, so in this uncoupled case, there is a unique solution. Now, this uncoupled case kind of misses a lot of the point of the problem, you could say, but there are interesting cases where this happens. So, for example, the CONIFOLD, which we saw right at the start of the talk, that is uncoupled. The form is 0. It's not finite in this sense. There were infinitely many omega gammas, but you can kind of just hold your nose and apply this formula anyway and see what comes out. So that's the first thing you can try and do. So let's think more generally than the CONIFOLD. We can apply this to coherent sheaves on some compact Calabi-Yau threefold. And we're only thinking about sheaves supported in dimension less than or equal to 1, so just curves. Mm-hmm. But if the form is just 0, I mean, when I wrote that, because yeah, I mean, the Euler form of that thing is 0, essentially because, you know, any two classes on any two classes on the CONIFOLD are supported on the curve, and curves don't intersect on a threefold. So essentially, yeah. So as long as you're restricting to curves on a threefold, the situation is always uncoupled. Why? It's going to give a nice answer in a minute. It encodes, I mean, it usefully encodes the solutions to the Riemann-Hilbert problem in, I mean, the Riemann-Hilbert problem is the solution is a function to the torus, and then you can compose with characters. So then you have a whole bunch of functions indexed by the, you know, by the characters of the torus, whereas this is just one function. So it's a more efficient way of encoding the solution. But I also think it's, you know, you'll see at the end of this slide why. Right, so what's going on here? So this can be made completely rigorous with stability conditions on the derived category of coherent sheaves supported in dimension less than or equal to 1. So constructing stability conditions on a compact Calabi-Yau threefold is a well-known, very difficult problem, which is starting to be solved now. But if you're just interested in sheaves supported on dimension less than or equal to 1, it's easy. You can easily write down stability conditions, and things are relatively well understood. So this would be the kind of Grothendieck group. This is where the classes of curves live. I'm going to take a central charge of this form, where this is going to be some complexified Kähler class. This has been computed. This is the BPS invariant counting points. These things are very much expected, but this is not known mathematically. In particular, we don't know that these BPS invariants are independent of n. Okay, this is a famous open problem, but it's expected that they should be independent of n, and that therefore, that they should agree with what physicists call the Gopakumo-Waffer invariant of genus 0. But this is not known, but at this level I'm happy to, I mean, there are plenty of cases where it is known. For example, on the CONIFOLD. And then, so what I'm doing here, sorry, is I'm just plugging that data into this formula and hoping for the best, because in theory this is an infinite sum, so things could go wrong. I think of it as h upper 6. So yeah, it will be h lower 0. Yeah. Okay, and so this is what you get. So there is this kind of fun calculation. You just put that previous formula into there, and this is what you get. And I must say, this calculation looks very similar to what Gopakuma and Vaffa were doing in their original paper. I have no idea whether this is related, but the sort of calculation looks quite similar to me. But let me just say exactly what's happening here. Well, firstly, what you're getting here is the genus 0, the contributions to the partition function from genus 0 Gopakuma-Vaffa invariants and from point sheaves. Okay, so that's what you're getting. And what's this positive degree business? When you expand this, you get some terms in T of degree -2 and 0. Yes, -2 and 0 corresponding to genus 0 and genus 1. You don't get that on the other side, so I'm missing that part of the partition function, annoyingly. But it was kind of inevitable by definition of my tau function and everything here. This is never going to have any negative terms in T. So that's definitely a flaw in what I'm doing. I need to weaken one of the assumptions about growth at infinity, I guess. Okay. So this is just, and I emphasize, this is just a formal calculation. I did not solve the Riemann-Hilbert problem. I just took what I knew would be the solution if there are only finitely many BPS invariants, and just took the formal sum and just saw what I got. And that's what I got, but it's it's an interesting answer. But you can, if you go to the special case of the resolved conifold, then you really can solve this Riemann-Hilbert problem rigorously. So we've already seen this, so let me just go through this quickly. Here again, we've got the same data, the resolved conifold. The only thing that's different from last time is that I'm taking a less arbitrary central charge. So I'm, in fact, taking a general central charge, which is going to map here's V and here's W. And I'm allowing V and W to vary more or less arbitrarily, except that I don't want the central charges of any of the branes to go to 0. So that's what these conditions here are. And in fact, this is basically the space of stability conditions for this example. Rather, the space of stability conditions is the universal cover of that. So now you can really, so we have an explicit jump for each of these rays, which is just exactly of this kind of form, not very complicated. And this ray is a rather more complicated ray because it has infinitely many BPS invariants on it. But nonetheless, there is a well-defined jump, and you can prove it converges on some analytic subset of the torus. So you're in business. You can try and solve the Riemann-Hilbert problem, and so. I'm not going to give you the full details here. They're in the paper on the archive, but there is a unique solution, and you can write it in terms of these special functions, Barnes, double and triple sine functions. And let me just say what the answer for the tau function is. So this is the answer I would like to have got, but just as I explained before, there is some cock-up in that you don't get the negative degree terms. So there are these two terms. This is genus 0 stuff. This is genus 1 stuff. And I'm not getting that, so I have to sort of kill that. But other than that, I'm getting this rather, to me, well, once you've stared at these for long enough, you start thinking these things are beautiful. And this is a unique function associated with the conifold, whose expansion at t equals 0 coincides with the closed string partition function. So you should think of this as, well, I would like to think of this as some non-perturbative partition function. And indeed, this precise expression does appear in the physics literature in a paper by Hatsuda. So, I think people have thought about these kinds of things. But to me, it's very interesting that you can get these things by thinking about these Riemann-Hilbert problems, which mathematically are just extremely natural. Once someone's given you DT theory, that's a very natural thing to think about. Okay, so I'm running out of time, so let me just skip to the last slide. So further directions. So what else are we trying to do? Oops. The next class to consider, I think, is these theories of class S. Gauter, Moore, and Knightsky wrote a very beautiful paper where they showed how to solve their Riemann-Hilbert problem by using the geometry of Hitchin systems, and obviously we hope to do the same, and it will be a rather similar story. It should be the kind of conformal limit of their story, but we're also wanting to, prove that there are unique solutions and so on. And I don't know how to do all this yet, but the basic picture seems to be that the space of stability conditions, I proved with Ivan Smith that the space of stability conditions for these examples is the space of meromorphic quadratic differentials, where you allow also the Riemann surface to vary. So the space is considered, you should have varying Riemann surface and varying quadratic differential. Quadratic differentials are almost the same as projective structures. Projective structures form a affine bundle over quadratic differentials. So you might prefer me to say oppers instead of projective structures. And then you can take the monodromy of those things. That gives you a map to the framed local systems, which is the cluster variety. And then the idea is that the Fock-Goncharov coordinates should give you solutions to this Riemann-Hilbert problem. So, I mean, I would love to be talking about this, but I really don't understand lots of details here. This is probably going to take another year to work this out. But that would be very nice if we could get some solutions. And I suppose, so what's the tau function going to be in that case? I guess it's going to be related to this, I don't even know the words yet, but this Nekrasov-Shatisvili limit of the, I mean, it should be to do with the generating function of the Opper locus, and yeah, there's a whole lot of stuff there, which I'm sure many of you can educate me about, and please do. Another thing that we're working on is wanting to generalize slightly. Yeah, this psi, I never really explained what psi was. The point is that the Riemann-Hilbert problem, what you would normally expect is a Riemann-Hilbert problem taking values in a group, right? So you should look for a map from phi from C star group, which jumps appropriately. That's what one would normally do. And the group in this case would be automorphisms of the torus. Now, this is an infinite dimensional group. I'm rather scared about thinking about functions from C star into some infinite dimensional group. So rather than doing that, I fixed my element psi in the torus, and I just evaluated this automorphism at psi, and I got myself a map to the torus. Right, so that's why I had to fix the data of a point of my torus at the start with. Instead of taking a map into a group, I evaluated this automorphism at the point psi to get an element of my torus. But nonetheless, you should now at least think about varying this point psi and understanding the behavior of that. And so we did solve the A1 case jointly with Anna Barbieri. We solved this A1 case. I mean, the formula's in a paper of Gato. I mean, it's not like we did anything radically new, but it's the same framework, and we just prove that there is a unique solution and study it. Yeah, so we want to bring out that analogy with finite dimensional Stokes behavior. And then the final thing I would like to say is that this problem, I keep asserting that we don't see the low order terms. This seems to be a tricky thing, actually, and it's very annoying because actually I didn't care about all these higher genus parts of the partition function. What I really wanted was the genus 0 part, because that's what gives me the variation of Hodge structure, right? So I really wanted the genus 0 part of the partition function. That's pretty much exactly the bit I don't get. And I think there's an interesting point here, which is that when I meddle with the beautiful formula by sticking in these extra terms, I kill a difference equation that this formula satisfies. So, I mean, in the A1 case, it's just the fact that the g function satisfies gz plus 1 divided by gz equals the gamma function. So there is some, the solution is given by gz plus 1 divided by gz. And I think that's the thing that one has to understand, and it reminds me of quantization. I mean, I think maybe to understand this, I need to do a quantized version of this Riemann-Hilbert problem. I'm not sure. I mean, if anyone has any ideas, please do let me know, but I'll stop there. Thank you.